So calculus with parametric curves. We're going to start with tangents. So this is differential calculus. All right, so suppose f and g are differentiable functions, and we want to find the tangent line at a point on the parametric curve that has parametric equations x equals f of t and y equals g of t. And we're sort of going to implicitly assume it's possible to write y as a function of x. We're not actually going to do that, but we are going to assume it. So the chain rule will give us that if y is a function of x, and I can kind of write this out, I know that the Leibniz notation can be a little confusing, but what we're assuming is that y is a function of x, which is a function of t. Then the chain rule would say if we wanted to take the derivative of y, that would be f prime of x times x prime of t, right? And that's exactly what this says in Leibniz notation. Well, if we wanted to find the slope of the curve at a given point, what we're looking for is dy dx. So we just want to isolate that dy dx. So to do that, we can just divide out the dx dt, and we'll end up with dy dx equals dy dt over dx dt. Meaning it's just the derivative of the y function with respect to t divided by the derivative of the x function with respect to t. And that's it, as long as dx dt is not 0. Usually, if dx dt is 0, what we'll have is a vertical tangent. But I'll point that out. We'll do an example of that. So it's a pretty straightforward formula, right? You can just almost think of it like dy dx equals this because the dt's would divide out and just give you dy dx. So pretty intuitive. All right, so let's go ahead and see how this works. Oh, sorry, before we do that, sometimes we're going to want the second derivative. Remember, that's just Leibniz notation for y double prime. And so all we have to do to find the second derivative is replace y in the derivative function with dy dx. And so what you end up with is ddt of dy dx over dx dt. So all I did was replace y in the first formula, or the formula for the first derivative, basically with y prime. So let's do an example. We have a curve C that's defined by the parametric equations x equals t squared and y equals t cubed minus 3t. We're going to show that it has two tangents at the point 3, 0, and we'll find their equations. Give you a chance to write that down. I'm going to open up GeoGebra, see if I can get my computer to explode. I'm running too many programs. T, and the point is 3, 0. I'm just going to X out of here to give myself some space. So X equals T squared, Y equals T cubed minus 3T. And we're looking for the equations of the tangents at 3, 0. And there's actually two of them. So we're going to go ahead and use our formula for finding a derivative, which was dy dx equals dx dt over dy dt. Oops. So first, let's make note of what dx dt is. That's just x prime with respect to t, so that's 2t. And then dy dt is 3t squared minus 3. And so dx dt over dy dt is 2t over 3t squared minus 3. All right, and so what we want to do is find the value of t that we can fill in at the point 3, 0. And so we can do that. Let's just take the x coordinate here, 3, and we'll just plug it in for x in our x parametric equation. And so what we end up with, right, is t squared equals 3. So solving for t, we're just going to get t equals plus or minus the square root of 3. So notice that we get two solutions there, which when we plug either one in here, that's going to give us two separate slopes, two values for dy dx. So let's look at dy dx, and I'll just say at t equals the negative square root of 3. So I'm going to get negative 2 root 3 over 3 times, when we square the negative square root of 3, we just get positive 3 minus 3. So that's negative 2 root 3 over 6, or negative 1/3 root 3, or I guess probably better to write it as negative root 3 over 3, right? All right, so there's my first slope at that point. And my second slope we're going to find by plugging in just positive root 3. So dy dx when t equals positive square root of 3. And that's going to be positive 2 root 3 over 3 times 3 minus 3, which just gives us positive root 3 over 3. So one thing I'll point out, we used the x coordinate to solve for t. We could have just as easily used the y coordinate, right? And we would have just plugged in 0 for y, and I would have ended up with t cubed minus 3t equals 0. So t times t squared minus 3 equals 0. So t equals 0, or t squared minus 3 equals 0. And from this one, notice that we would just end up with the exact same, plus or minus root 3. All right, now last thing they said, write the equations of the tangent lines. So I'm just going to do that. I'll just use point slope form. So y minus 0 equals the slope negative root 3 over 3 times x minus 3. And y minus 0 equals positive root 3 over 3 times x minus 3. So let's just verify that. I'm just going to show you in GeoGebra here. This is our curve. It's just a little loop. And so the point we were talking about is actually the point where that loop crosses itself, which is 3, 0, right there. And so one of them was y minus 0, so just y equals negative square root 3 over 3 x minus 3. That definitely does not look tangent. Oh, hold on. No. Oh, I did something wrong. You guys see a mistake? Good thing we checked it graphically. Hold on. So x prime is just 2t. Y prime is 3t squared minus 3. 2t over 3t squared minus 3. T equals plus or minus root 3. Huh? What am I doing here? All right, all that's going to do is our answer is going to be the reciprocal of itself, which if you take the reciprocal of this, it's just negative root 3. Sorry about that. And so this should just be positive root 3. So that's just going to change my slopes. Everything else stays the same, but that's why we check our answers graphically, if we have the ability to do so.
I think you have to redo your master's degree, Mr. Toller.
God damn it, that's going to take me forever. All right, so now let's go back to GeoGebra. Y, oh, just delete this altogether. Okay. Y equals negative square root of 3. There we go, times x minus 3. That looks tangent. And then y equals the positive square root of 3 times x minus 3. Also looks tangent.
Why wouldn't it be negative 3 over root 3? Why is it just
Sorry, say again, Claire.
why wouldn't it be negative 3 over root 3? Like, why does it just
It would be, but if you rationalize that, so hold on. I was just trying to change the colors to make it more obvious. All right. So if you rationalize 3 over negative rad 3. So if I multiply top and bottom by rad 3, we end up with 3 rad 3 over negative 3, which is just negative rad 3.
Oh, gotcha.
Yeah. All right, sorry for that blunder. Let's go back to this. B, find the points on C where the tangent is horizontal or vertical. Okay. So we're still looking at, I have x equals t squared, y equals t cubed minus 3t. We found out that dy dx is in fact 3t squared minus 3 over 2t. So let's talk about where the tangent is horizontal. That's going to be when the slope is 0. So for a horizontal tangent, I'll just set my derivative equal to 0 and solve for t. This is basically I can just multiply the 2t over to
What?
Your laptop.
My surface?
Yeah.
other side. Multiply the 2t over to the other side, so we just end up with 3t squared minus 3 is 0. And then we just want to solve for t, right? So add 3 and divide by 3, we get t squared equals 1. So t equals plus or minus 1. All right. So now we don't just want values of t. T is our parameter. We want x, y coordinates. So I'm going to take that value, both values of t.
No, not Barbie.
Sorry, guys. This is chaos. And I'm going to plug it into my parametric equation. So let's just start with t equals 1. Right? So when t is 1, if I plug it in for x, I just get 1. And if I plug it in for y, I get negative 2. Does that make sense? And then we'll just do the same thing for negative 1. When t is negative 1, I'll plug it in for x, I still get 1. I plug it in for y, I get negative 1 plus 3, so positive 2. And again, let's check this graphically, just to make sure it looks like it makes visual sense. So I should have horizontal tangents at 1, negative 2, which just visually, yeah, looks like a horizontal tangent there to me. And then also at 1, positive 2. And again, horizontal tangent up there. That makes sense. All right, vertical tangents. Those will occur basically when our denominator is 0. I say basically because it technically has to be when the denominator is 0 and the numerator is not 0. So 0 over 0 is technically an indeterminate form. But what you want to do is set your denominator equal to 0 and solve. And then just make sure that value of t doesn't also make your numerator 0. So setting my denominator equal to 0, that's just 2t. 2t equals 0, easy enough. T equals 0. We already know that t equals 0 is not a value that makes my numerator 0 because we already solved for the horizontal tangents, which was basically setting the numerator equal to 0, right? All right, so t equals 0. If I plug t equals 0 into my parametric equations, I'm going to go ahead, what am I going to get? I get 0, comma, 0. So these are my horizontal tangents, and this is my vertical tangent. Let's just again verify that graphically. So 0, 0 is just the origin, and you can see there is clearly a vertical tangent there. All right. So let's keep going.
Wait, I have a question.
Go ahead.
So for the horizontal tangents, we set the entire thing to 0, and then vertical.
Just the denominator.
0.
Determine where the curve is concave up or down. Do you guys remember what we have to look at to determine concavity? It's been a while. That's in Calc 1. Eva with a hard pass on that. Nobody. Tommy, you got it.
The double prime.
Yeah, the second
Right.
derivative. Yep. Good. Yeah, good, Eamon. It's the second derivative, and it's just the sign of the second derivative. When the second derivative is positive, we get that upward concavity. And when it's negative, we get downward concavity. So we want to take a look at the second derivative. So I have to start over because I stupidly did not just put a blank slide in place. All right, so x is t squared, y is 3t cubed. No, just t cubed minus 3t. So the first derivative was 3t squared minus 3 over 2t. And the formula for the second derivative, d2y over dx squared, for parametric equations is d dt of dy dx over dx dt. So the first thing we need to do is take the derivative of the first derivative with respect to t. All right. It's not a huge issue. I'm going to avoid having to use the quotient rule by just simplifying this algebraically before I take the derivative. So I'm just going to break this up to 3t squared over 2t minus 3 over 2t. And then I can rewrite that as 3 over 2 times t minus 3 over 2 times t to the negative 1. Right? So now when I take the derivative of that, so I'm going to do basically d dt of that 3 halves t minus 3 halves t to the negative 1. And that's going to be 3 halves minus, nope, plus 3 halves t to the negative 2, right? And that just goes over dx dt. So I have 3 halves t, no, sorry, 3 halves minus 3 halves t to the negative 2. No, plus. Good Lord. And that's over dx dt. And dx dt was just 2t. All right, but now I have to do a little work to clean this up. So this can be written as, let's see, if I factor out the 3 halves, that's 1 plus t to the negative 2, or 1 over t squared, right? Over 2t. So then that's 3 times 1 plus 1 over t squared over 4t. And then I want to get rid of that fraction in the numerator. So if I multiply top and bottom by t squared, I can kind of do that, right? And that'll give me 3 times t squared plus 1 over 4t cubed. So all that algebra makes sense to you guys? All right. So now, concavity. We have our second derivative here. To determine concavity, we need to know where our second derivative is positive or negative. And so we just want to think about what separates the positives from the negatives. 0, right? So first, let's solve for where our second derivative is equal to 0. So we'll set it equal to 0. And we'll solve. This is basically just going to eliminate my denominator. If I multiply both sides by 4t cubed, that's gone. So what I just end up with is my numerator, 3 times t squared plus 1 equals 0. Divide out the 3. And now I'm realizing this isn't going to help us because there are no real solutions to this. All right. So let's just focus on this. Let me go back. So t never equals 0. But just by inspection, if t is positive, what will the second derivative be, positive or negative? So you can just test that. Like if we plug in a positive value for t, like 1, the numerator is positive, the denominator is positive, the second derivative is positive, right? So that's going to imply that the curve is concave up when t is positive, right?
This, no.
Okay. And then likewise, if t is negative, notice that the numerator, like if you plugged in -1, because we're squaring it here, the numerator is still going to be positive, but we're cubing it below, so the denominator is going to be negative. So the second derivative ends up being negative in that case. In which case, it's concave down. And so it's hard to see in GeoGebra because GeoGebra, unlike your calculator, doesn't graph it out using t steps. So it doesn't like graph it out by graphing points of t, but basically this top half of the curve, these are all your negative values of t. That's where it's concave down. And then this piece of the curve, these are all positive values of t. That's where it's concave up. Part D just says sketch the curve. We've already done that, so I think we're good. All right, any questions over that example? All right, I need a water. Let's talk about areas. So in general, you guys know how to find the area under a given curve. Let's say my favorite generic curve there. Let's say that's y equals capital F of x. Then we know that the area under that curve is the integral from a to b of f of x dx, right? So now let's say that x and y are actually defined parametrically, where x is f of t, and y is g of t. So the other thing I want to point out really is that this is just equivalent to the integral from a to b of y dx, right? Because y is equal to f of x, so I could either write f of x here or y there. But if I put y there, it'll make it a little bit more clear, I think, what I'm doing to get this into a parametric integral. And so I'm basically just going to use a regular substitution. So I'm going to replace y with g of t. So this is the integral of g of t. Now I need to replace dx. Well, dx dt, that's just the derivative of x with respect to t, so that would just be f prime, right? So then if I separate the differentials and I multiply dt to the other side, I have dx is f prime of t dt. So that's what I'm going to replace dx with. I'm just going to replace it with f prime of t dt. And then I would update my limits of integration just like you do with a u substitution, right? If you don't want to go back to terms of x and you have a definite integral, you can update your limits to be in terms of u. So I would update my limits to be in terms of t, and I'm just going to say that they are alpha and beta, where t traces out the curve between alpha and beta. There you go. So this is basically my equivalent parametric equation integral, and that will let me find the area underneath or enclosed by any parametric curve. All right. So last time we developed these parametric equations for a cycloid, which is the curve traced out when you follow a point on a circle. And now we want to find the area under one arch of the cycloid. Okay, so we will just start with our area formula, which is the integral from alpha to beta of g of t times f prime of t dt. Remember that x equals f of t, y equals g of t. All right, so now let's put it in the context of what we have here. So this is going to be the integral of the y parametric equation. So that's r times 1 minus cosine theta times the derivative of the x parametric equation. So first let's figure that out. X prime, right, would be r times, theta is my parameter, so I'm basically differentiating with respect to theta, so that would be 1 minus cosine theta. So times the same thing, times r times 1 minus cosine theta d theta. Now my original integral, so let's just, if we were integrating this with just respect to x, my integral would be from 0 to 2 pi r, yes? Of whatever that function is, dx. So now I need to get my limits here to be in terms of t. Right now, those are limits in terms of x. So what I want to do that, I just want to think about when, I'll say when x is 0, and so if I plug in 0 for x, I would have 0 equals r times theta minus sine theta. R is a constant, so we can just divide that out. So I have theta minus sine of theta equals 0. And so we have to solve for theta here. Not so easy maybe to do by hand, but you can actually do this one by inspection. Is there any value of theta where theta minus sine of theta would be 0? What's sine of 0? Yeah, Tommy, you got it. So if we plugged in 0, that works, doesn't it? Because sine of 0 is 0. So theta equals 0. So that may have felt like a bunch of work for nothing. But we had to do it. So my lower limit is still 0, basically. My upper limit, I'll say when theta, or sorry, when x equals 2 pi r, I have 2 pi r equals, same thing, r times theta minus sine theta. The r's divide out. And I get, theta minus sine theta equals 2 pi. Any guesses for that? This one we're going to have to solve by inspection as well. Go ahead, Tommy.
Is it 2 pi?
Mm-hmm. Good work. Because if I plug in 2 pi, I would have 2 pi minus sine of 2 pi. Remember, the angle 2 pi is the same as it's coterminal with 0, so sine of 2 pi is just 0. So 2 pi minus 0 still gives me 2 pi, which is what I wanted, right? So my upper limit is 2 pi. All right. So we have the integral from 0 to 2 pi of r squared times 1 minus cosine theta quantity squared d theta. Okay, r squared is a constant. So that can come out. And I have run out of space. So let me do this. All right, so integral 0 to 2 pi. Pulling the r squared out front, and we have 1 minus cosine theta quantity squared d theta. All right, we're going to FOIL that out, 0 to 2 pi. It's going to be 1 minus 2 cosine theta plus cosine squared theta d theta. Okay. Before we go ahead and integrate, I'm gonna use that half angle formula that's in your trig cheat sheet to replace cosine squared theta with 1/2 1 plus cosine 2 theta. So this becomes r squared times integral 0 to 2 pi 1 minus 2 cosine theta plus 1/2 times the quantity 1 plus cosine 2 theta d theta. And then I'm going to do some combining like terms.
Isn't it 2 cosine squared theta?
No, it would just be here. Are you talking about here?
Oh, sorry. I saw the arrow going down and got like.
I'm
confused.
sorry. I got you. That arrow should actually be pointing here. That's just a trig identity. So then 1 minus 2 cosine theta plus 1/2 plus 1/2 cosine 2 theta d theta. And then I have the 1/2 and the 1 that I'm just going to combine to make 3/2 minus 2 cosine theta plus 1/2 cosine 2 theta d theta. Okay. All right, so now I'm ready to take the antiderivative, right? So that's going to be 3 over 2 theta plus 2 sine theta minus 1/4 sine 2 theta from 0 to 2 pi. All right, plugging in 2 pi to that first term, the 2's will divide out, so I'll just end up with 3 pi. To the second term, sine of 2 pi is just 0, so that's 0. And to the last term, that would be sine of 4 pi, or negative 1/4 sine of 4 pi is also 0, so that's minus 0. And then when I plug in the 0 to all of these, we still just get 0 for everything. So I'm really just left with 3 pi. And we have the r squared out front, 3 pi r squared. So pretty interesting. The area under one arch of a cycloid is actually just 3 times the area of the circle used to trace it out.